Hey everyone, so this is going to be the last thing to talk about in the terms of energy. We've already talked about some of the different types of energy, and we talked about conservation of energy, which I said was the bulk part of this unit. However, I've been neglecting the last type of energy that can be thrown into the mix, which is spring energy. Now, the reason why I'm saving it for the end is because first, I want you to focus mainly on trying to deal with the conservation stuff in the context with just potential and kinetic. Once you kind of understand that and you have a good grasp on that, adding in spring energy just makes it a little bit easier. Dealing with it right from the get-go can make the entire thing a little bit more tricky, but it's also because of the fact that spring energy is actually not super common. It's rarely used. It sometimes pops up. And a lot of times it's usually by itself. That's why I kind of left it to the side was I didn't really want to add it in when it's not going to be a main thing to talk about. So I want to leave it by itself. Now, the idea here is we now are going to talk about the energy that can be stored within elastic objects. So objects like springs or rubber bands that could be stretched and stored energy in them. Now, here, it's actually kind of very similar to gravitational potential energy, where we said that an object raised to some height will have some sort of stored energy that can be turned into something else, like kinetic energy or heat eventually, because of that force of gravity constantly pulling the object down. Here, what we have is that an elastic object, can be either stretched or compressed, and that energy will be stored in that compression or expansion. I'm just going to use one of the terms, but keep in mind that whatever we talk about, it works for both compression and elongation. So when we compress a spring, that energy can be stored in that compression in the form of spring potential energy. And just like with the gravitational potential, that's caused by the force of the spring trying to get rid of that compression, to kind of push against you. So that's how it's being stored. It's being stored in a force within that spring. And we end up giving this a qualifier of U subscript S. So this would be spring potential energy. We could think about what factors might affect the energy being stored in spring. Now, we haven't actually talked much about springs and spring forces. So this kind of ends up hitting both of those. Now, the amount of energy stored within the spring easily can be defined with or based off of how much that spring is stretched. Just like how the height, the greater the height, the more gravitational potential energy. However, it also depends on how rigid the spring is. If you have a spring that is extremely rigid, then compressing it a little bit is going to store a whole lot more energy than a very loose spring compressed the same amount. Perfect example is if I take a very loose slinky and I stretch it out a meter long, I'm not really storing much energy within it because the slinky is fairly loose to begin with. But if I take a spring within a bed frame, or the spring in a car, and I stretch to that same meter, that spring is significantly more rigid and requires a significant amount of force to act on. So that force to stretch it to that distance is going to result in more energy being stored when I finally release it. Uh, the rigidness for a spring is represented by the symbol K for spring constant. So K is an inherent trait to a spring. So a spring can have a spring constant K. It will be constant throughout its life for the most part. But different springs could have different spring constants. Just keep that in mind. So the spring constant refers to how rigid the spring is. The greater the value of K, the more rigid the spring is. And X is being used for the displacement that the spring experiences. And again, this displacement could be in either direction, either compression or elongation. It's honestly not really going to be differentiated in this class. The spring constant is measured in newtons per meter, and the displacement is measured in meters. So the energy stored in a spring is given by this equation, US equals 1/2 kx squared. So this is the equation. It's going to be 1/2 of the spring constant times the elongation squared. You may notice this looks very similar to the kinetic energy equation, 1 half mv squared. Again, we kind of talk about this. Well, I didn't say it here, but once again, this is derived through the exact same way that all other energy equations are come from, which is the work equation. We could take the work equation, we can manipulate it and adjust it to get this by using the spring force as far as uh, what's acting on the spring as we stretch it out. This is just an example that the idea that as we stretch a spring or we compress a spring, we kind of store energy, and this energy, the elongation, the x value, is based off of the from the point of rest for that spring. So x does not represent the length of the spring; it represents how much the spring is stretched from its original position, from its rest position. Okay. So here is our first question. Pause video or yourself, and we'll go in a second. All right. So we're looking for the spring. We're given a spring constant, and we're told how much it compresses. We want to know what the energy being stored in the spring is. So we plug our numbers in and chug our answer to be 62.5 joules. Now, one thing I forgot to mention was that there is a spring force equation. There is a force uh, given based off of the spring constant and the how much elongates of how much force that the spring applies. However, we're not going to talk about it right now. We're going to talk about that in more detail when we get to the unit of simple harmonic motion. So we'll discuss that later. For now, we're just focusing on the energy aspect for springs. And really, all this is going to allow us to do is make our conservation energy problems just a bit more depth. So instead of going straight to an object having speed, we can now have it compress a spring, and then that now can give these object speed. So we've had problems where we just said, oh, the object has some speed as it goes up a ramp. Well, now it's going to compress a spring, and that spring is going to release to give the object speed as it goes up a ramp. So that's really all it is that we're just adding another factor to the mix. All right, and here's a perfect example. So pause the video, work yourself, and we'll go over in a second. All right, so as I've said before, one main aspect to do is to keep track of what's going on at all these points, all these different moments, and keep track of all the different types of energies that are involved in the scenario. So first question is how much does the spring need to be compressed just for the block to reach this the height of 10 meters? So if we think about what's going on, when the spring is compressed, that moment at H1, the object has both gravitational potential energy and it has spring potential energy. When it gets to H2, it says that it just reached the top of H2, which means that the velocity at this point is zero because it just reaches it. So the type of energy it has at H2 is strictly gravitational potential. So we're going to set those two energies at H1 equal to H2. Uh, I should have also mentioned that, as I said before, that when you do gravitational potential energy, it depends on what you define as zero. If you set the ground to be zero, then your equation would look different than mine. It would be UG1 plus US equals UG2, where we're saying the UG1 being height 1 and UG2 being for height 2. However, another way that we could say is that just like how we kind of did it in some of our previous problems, we could say that height 1 is our zero line, and we're going to do all the heights from there. So for this specific part at least, we're going to say that at H1, there's no gravitational potential energy because that's the lowest point. It's only spring potential. When it gets to H2, it's now going to have gravitational between H2 and H1. So because H1 was originally 5 meters, H2 is 10 meters, the height difference is going to be 5 meters. So I plug this in, and I end up getting the answer to be 1.58 meters. Again, you can get this the same way. If you had said that the ground was zero, you would have had an MGH of 5 times 10 times 5 on the left hand side, and the right hand side would have been 5 times 10 times 10 for H2. But you should still have gotten 1.58. All right. The next part, part B, it says if it continues all the way to H3, what is the speed of the block? So again, I now have what I can do is with the flow of energy, I can either set any 2 points here equal to each other, because the idea being that the energy is constant and conserved throughout this entire problem. So the total energy at any point is going to be equal to the total energy at H3. I could do at H1 and set it equal to H3. I could do it to H2 to H3. Personally, what I like to try to do is find a point that has the least amount of energies available, again, just to make my life easy. So what I'm going to do is I'm going to set H2 equal to H3. H2 strictly only has gravitational potential because, again, it just reached the top. So it's reaching the top. That's its maximum height. There's no kinetic energy. It only has gravitational potential. And then it goes to H3. Now, if I'm setting the ground equal to 0, H3 would have both potential and kinetic. Or I can set H3 as my new 0 line because, again, as long as I'm consistent for a specific part, I can change what I'm setting 0. So I can say H3 is 0 now, and I could do the height difference and say that this now only has kinetic energy. So that's what I'm going to do here. H3 is now going to be 0. So this is at 2.5. That means that my H2 is going to be at a height of 7.5. So plug that in, and I end up getting that the speed is going to be 12.2 meters per second. Again, you could do whatever you want as far as what energies you want to set equal to each other. You could have set this point when the spring was compressed at H1 equal to H3. That also works. If for some reason you found this point, you could set those 2 points equal to each other. Again, it's whatever floats your boat. Here's the next one. Sketch the bar graph that represents the energy transfer from H1 to H3. Pause video work stuff, and we'll go over in a second. Now, you might notice that there's an H1 compress and H1 release. The idea being that there's two moments in H1 that's happening. There's the part where the spring is compressed at H1, and then there's the moment right after the spring releases. What's happening? So you'll see what the difference there is. So the easiest thing to do is just to start off with the amount of gravitational potential energy at H1. That kind of makes life a little bit easier. Just set that as a standard, and we're going to go through all of them and just do gravitational potential for all of them. So H1 kind of starts at 5 meters, so we're just going to set that equal to 2 blocks, let's say. When it gets to H1 release, that doesn't change. It just kind of moves horizontally, so it's not gaining any height, not changing its gravitational potential. When it gets to H2, the height doubles, so it goes from 5 meters to 10 meters. So that means instead of having 2 blocks, it's now going to gain to 4 blocks. And then we're going to go to H3, where it's going to go down to half a block because it goes from 5 meters to 2.5. So it's only going to be 1 block of UG. So this is the flow of energy. This is the gravitational potential energies. Now, one thing to keep in mind is that at H2, there is no other type of energy besides gravitational. So because I have 4 blocks dedicated to the gravitational potential energy, that also means is that the total energy in the system is 4 blocks, right? So when I set up my blocks for all of these, I need to make sure that I do not exceed or I do no more or no less than 4 blocks in total. So going back to H1, I know that some of the energy is also stored in the form of spring potential. Well, I know 2 of my blocks are dedicated to gravitational. The other 2 to get me to 4 blocks have to be spring potential. When I go to H1 release, well, now the spring potential is gone, but my gravitational is still 2, so that didn't change. So where did the spring potential turn into? It turned into kinetic energy. So that 2 blocks now turns into kinetic. Going back to H3, there is no spring involved, so all the blocks end up going in the form of kinetic. 1 block is dedicated to gravitational already, so that means 3 blocks are dedicated to kinetic energy. So this is what the bar graph ends up looking like for the energy transfer. You want to keep track. This is kind of the way that you go about it. Starting with the gravitational is always the easiest one because of the fact that there's a linear relationship between gravitational potential and height. So you can easily keep track of what the energies are. And then, just as I said, as I showed, I used my knowledge of H2, the idea that this point has only the form of potential energy, to determine how many blocks of energy I'm allowed, and use that throughout this process to extrapolate and figure out how much blocks of energy were in each form, kinetic and potential, spring potential. That's pretty much it for now. We'll do some of the other questions in class. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.